So I think last year you have plenty of lectures with regard to the membranes, physiology, and we have focused also on the membranes of excitable cells. So for about 15 minutes we will review what you have taken last year, but you will have these lectures online also, and you can go through these lectures to review what you have taken last year. In addition, you will have some short notes with regard to the excitable membranes, also short notes with regard to muscle physiology. Okay. So what you remember about last year? You are finding this information with regard to the membranes of excitable cells and Guyton, your reference book, and these are the editions and pages where you are finding this information. I think you know that muscle and the motor neurons, both of them, they are excitable cells, in addition to many other excitable cells, but we are focusing on these structures. You will know that to get the muscle contracting, finally, we have stimulus coming from motor neurons, which exciting this muscle to get the contractile process. Okay, this is a representation, the first one, okay, here is a representation to a motor neuron, actually. So we have cell body at the level of the spinal cord. We have long axon toward the muscle, and we have many terminals at the level of the muscle. For each terminal will end with a muscle cell, one muscle cell, okay? Forming a specific structure, it's like synapse, but we are not calling it synapse, and it is called neuromuscular junction. What we have at these terminals, we have neurotransmitter, which is known, the motor neuron, released, and that neurotransmitter is acetylcholine, okay? So once it's released, it's acting over the muscle to get stimulation of that muscle, and we are getting the contractile process. So what we will be learning, how the process of contraction is taking place, and the whole process is called excitation-contraction coupling. Okay. Okay. So what's the property of the membranes of excitable cell? All these membranes actually, at any cell, they are separated in two compartments. We have extracellular and intracellular. These information, you know them, but we have differences in the composition of ionic composition between these compartments. And at the level of excitable membranes, we have properties that these membranes are permeable, having differences in permeabilities with regard to these ions, which results in generation of what we are calling resting membrane potential, -70, -80, -90. So this, once it is established, we have these cells. They are called excitable cells. Now, other property of the membranes of excitable cells, they can generate what we are calling action potentials. I think you know from the last year how we are generating action potential at the level of the excitable cell. Okay, sorry. We said we have differences in permeabilities, and the potential which can be created depends what types of channels are more active or less active. What we can calculate the potential, the equilibrium potential for each ion by using this equation, if you remember it, which is called Nair's equation, okay? And this is the equilibrium potential. For example, for potassium is equal to 61 multiplied by concentration of potassium outside over the concentration inside. Also, you can calculate it for sodium. In this case, you are changing the concentrations according to the concentration of each ion. But if you would like to measure the potential which is created by permeability for many ions, we are using another equation, which is called Goldman-Hodgkin-Katz equation. You remember it from the last year. We said that these membranes are equipped with channels. We have sodium channels, potassium channels, and so on. I think you know we have many types of channels. Some they are called ligand-gated channels, some others they are called voltage-gated channels. You know the properties of the ligand-gated channels, so we are needing neurotransmitter or any ligand to open them, okay? You will see these types of channels at the membrane of the muscle, for example, the ligand-gated channels. But also we have a lot of voltage-gated channels. So what's the property of these voltage-gated channels? Once we have changed the resting membrane potential to a less negative potential, we can get activation of these channels, okay? We will see their properties and what happens by activation of these channels. I think you know by activation of potassium channels, what we are getting more negative potential, and what we are calling it hyperpolarization. By activation of sodium channels, we can get depolarization in this case, and that process we can also generate what we are calling action potential. If you have depolarization reaching a point which is called the threshold, okay, if you remember it, at that point you have activated almost all voltage-gated sodium channels. You are getting much faster diffusion of sodium from outside to inside, and you may revert the potential, the membrane potential, and reaching positive values for that membrane potential, as you see here, okay? More than zero, the membrane potential. And the membrane potential is measured as inside with regard to the outside, if you remember. These are the phases of that electrical changes that are taking place, which is called the action potential that we can have. Now, in motor neurons and in skeletal muscle, we have these two types of channels. The sodium channels and potassium channels are involved in getting changes in the membrane potential. We are not having the calcium channels involved, okay? At that level, we are not having them. But you may see that the calcium channels are involved at the terminals, at the neuromuscular junctions, okay? You will see that. We are getting activation of calcium channels, but these calcium channels are having another role, to get entry of calcium toward the terminals and to get the release of neurotransmitter, okay? But during action potentials, at these excitable cells, we have only sodium and potassium channels which are involved. I think you know during this fast depolarization, which we are calling it as threshold, as pairing stage, we are getting highest activity for sodium channels, and during repolarization, we have highest activity for what type of channel? Potassium. Okay? How we are bringing the potential from the resting membrane potential to the threshold depends. You can get activation first, okay, but not all the time. by activation of chemical gated channels to get depolarizations, and these depolarizations, by summation of these depolarizations, you may reach the threshold in this case, okay? And at the axon, what happens? You have currents, if you remember, okay? So we have like electrical stimulation, these currents causing depolarization of the nodes, for example, and we are getting generation of action potentials at the node of RAM A. This is again the configuration of action potential. That point is the threshold, fast depolarization, which is called also firing stage. Then we have repolarization and so on. Sometimes we are, لو سمحتوا please ما تشوشوا على زملائكم. We are recording this wave after the potential, which is called positive after potential or after hyperpolarization. So you can review all these points by yourself to understand what happens at the level of excitable membranes during action potential. We said we have sodium channels involved and potassium channels involved. But if you are looking to the activity of sodium channels, we can find them in 3 states, okay? The first state during resting potential and during depolarization until reaching the threshold. We are talking here about the voltage-gated channels, okay? They can be found at the state of closed and capable for open. Then once you have reached the threshold, they are becoming open. During repolarization, they are closed and not capable for opening. And these 3 states are defining the 2 periods that we, if you remember them, we have refractory period, we have the absolute and the relative refractory period. So now at the threshold here, actually we are starting activation of the sodium and potassium channel, but the rate of activation of sodium channels is much faster than the rate of activation of potassium channels. Once you have reached the resting potential or near the resting potential, you are inactivating potassium channels. At which point you are inactivating sodium channels actually. Once you have reached the positive potential, okay, positive inside with regard to the outside, resulting in inactivation of these voltage-gated sodium channels. So we have fast activation and almost fast inactivation of these sodium channels. Why? The activity of potassium channels is much slower, okay, activation, but we have somehow fast inactivation of these potassium channels. Okay. Again, if you are relating these to the action potentials, so this is referring to the activity of sodium channels, it's mostly coinciding with the firing stage of action potential. Okay, once you have reached positive potentials, you are inactivating sodium channel, while the activity of potassium channel, the highest activity for these channels is during repolarization process. The highest activity for potassium channel is coinciding with that unit of action potential. So these are the points that I would like to review with you, only to remind you. You can go through the details in your notes and in your reference book to understand what's going on. This is a representation, also can be a representation for a motor neuron. We said we have cell body, we have long axon. What type of axon is myelinated axon, okay? And at the cell body here, at the axon halo, we are generating action potentials, and these action potentials spreading along the whole axon until reaching the terminals. And don't forget that these terminals are having neurotransmitters, which is known as acetylcholine, released upon having this action potential reaching these terminals. You will see the mechanism also in detail. And how we are getting propagation, what type of conduction along these axons is saltatory conduction, okay? So this is, and at the terminal we said we have release of neurotransmitter. Now at the muscle membrane, we have specific receptors for acetylcholine, and we are calling these receptors as nicotinic receptors. You will understand why we are calling them nicotinic receptors when we are talking about excitation, contraction. Now the motor neuron is receiving many inputs, many presynaptic terminals are synapsing with these motor neurons. Most of these synapses, presynaptic, or most of the presynaptic terminals, they are inhibitory. So they are trying to keep the motor neuron quiet without getting generation of action potential. But if we are needing the muscle to move, for example, then we are getting more excitatory inputs to reach the threshold to generate action potential, which can spread toward the muscle and causing activation or stimulation of the muscle to contract. Okay? Now, the inhibitory potential, the presynaptic for the motor neuron, okay? They can cause hyperpolarization, as you see, so generating what we are calling inhibitory postsynaptic potentials, while the excitatory potentials, okay, or while the excitatory presynaptic terminals, they can generate excitatory potentials. These are not action potentials yet, okay? Some they are calling them as sub-threshold potentials. But what happens at the motor neuron, we can get summation of these potentials. We have two types of summation, if you remember. We have spatial summation and temporal summation. By these summations, we can reach the threshold. Once you have reached the threshold, the motor neuron then can generate the whole action potential, which can spread toward the terminals. Okay? I think you know the differences between the spatial summation. So we have two presynaptic terminals, for example, which can generate two excitatory potentials, for example, okay, that can sum with each other to reach the threshold. While in temporal summation, we have one presynaptic input, which can cause depolarization. Then we have another action potential coming from the presynaptic neuron to cause more depolarization at the postsynaptic membrane, and so on, to reach the threshold and to generate action potential. So this is a summary what we have, okay, at the motor neurons. Slide representation here, for example. Many presynaptic neurons, some of them, most of them, they are inhibitory, but some they are excitatory, so they can cause generation of action potential at the motor neurons. If you have questions with regard to this summary, so we will start with our lectures. We have finished one chapter. Okay, you have a question? Questions? Which you other? Okay, I hope so. So we are starting talking about muscle. We have 3 chapters there, chapter 6, 7, and 8. First of all, these chapters are talking about types of muscle. I think you know we have what we are calling smooth muscle cells, we have striated muscles. We have a lot of differences, even functional differences between all these types of muscle, the smooth and the striated. Even the striated muscle, we are finding skeletal muscle and cardiac muscle. In both of them they are striated, but we have also a lot of differences, structural differences, functional differences between the cardiac and the skeletal muscle cell. Today we will focus more on skeletal muscle cell. With regard to cardiac muscle cells, you will be taking them when you are taking cardiovascular system to understand the exact function of these cardiac muscle cells. With regard to the control, I think you know we can have voluntary control over muscle, we can have involuntary control over the muscle. Like smooth muscle cells are having involuntary control, while skeletal muscle cells are having only voluntary control. Cardiac muscle cells, involuntary controls. Okay? So, if you are doing the muscle, we have to talk something or some points with regard to structure. I think this slide much better. So the whole muscle is composed of what we are calling muscle fascicles. What are these fascicles? A group of muscle fibers. What we mean by muscle fibers is we're referring to one muscle cell. Muscle fiber. Some they are calling them myofibers also. Myofibers, which is referring to one muscle cell. Okay? So these fascicles, you have a lot of muscle fibers. This is one of them. If you are magnifying that one, you are getting this muscle fiber. Everything here is one muscle fiber. Okay? Inside that muscle fiber, we have a cylindrical-like structures, as you see, which are called myofibrils. Myofibrils. So you have to differentiate between myofibers and myofibrils. Myofibrils are cylindrical structures inside the muscle cell. What's the appearance of these myofibrils? As you see, it is striated appearance, which is giving that striation to the whole muscle fiber area. Okay? Why we have that striation? Because we have a specific organization of contractile proteins which are giving that striation. We'll see today how these contractile proteins are organized to form myofiber. This is part of the myofiber, as you see. We have 2 types of filaments, which are the contractile proteins, forming the myofibril. Okay? So we have what we are calling thin filaments. Your phone, please, off. Okay? And you have thick filaments. Thin filaments and thick filaments, which are forming the whole structure of myofibrils. Now, if you are viewing the thin filaments, we have a structure here which is called Z-discs, protein structure, which are holding the thin filaments, okay? Held by that structure. Now, the distance between the 2 Z-discs, the 2 nerve Z-discs, is called sarcomere. That's the sarcomere, which is the contractile unit at the level of muscle. Okay? Now, these Z-discs are located where? In the middle of the lighter region. You know now the striation, by that striation we have darker region and lighter region. Okay? So in the middle of lighter region here, we have these Z-discs. That lighter region is composed of What we have there? Only thin filaments. Okay? But in the middle of that we have the Z discs, while the dark region is thick filaments plus some overlap by thin filaments. Okay? So we have there, we have thick filaments, and we have also thin filaments which are overlapping these thick filaments. Okay? Now this is a structure of thin filament, and this is a structure of the thick filaments. Now, again, here you have thick filaments, here you have the Z discs, okay? As you see, that's the lighter region, which is called the I band. The darker region is called the A band. From where it is coming, these names, I band and A band. Sorry. Isotropic band and anisotropic. Okay? So because of that, they are called A band to refer to anisotropic band and isotropic. Isotropic, we have similar, the same structure. We have only thin filaments, while anisotropic, we have thick and thin filaments here. Okay? Now, this is the whole muscle again, which is called the myofiber. That myofiber is having a membrane, okay? Muscle. It's muscle membrane or cell membrane. But we are calling that cell membrane as sarcolemma. That way it is called sarcolemma. Also, we have high representation of endoplasmic reticulum inside, and this structure of endoplasmic reticulum is called cytoplasmic reticulum. Okay? The cytosol of the muscle cell is called sarcoplasm. Now you know what we mean by sarcoplasm, what we mean by cytoplasmic reticulum, what we mean by sarcolemma. Okay? So these are names, لو سمحتوا please, for these structures at the level of muscle fiber. Okay. Now returning back to the myofibril, as you see, we have darker regions and we have lighter regions. We said in the middle of the lighter region, or which is called the A band, in the middle of that I band, sorry, we have the Z discs, and the whole structure between two Z discs is called sarcomere. Okay? Now, you have here region where you have overlap between thick and thin filaments, and it's called zone of overlap, but also you can have a region where you have no overlap between thick and thin filaments, and we are calling it as H zone. That's the H zone. Okay. Now, by contractile process, what happens? We have interaction between thick and thin filaments. That interaction results in pulling the thin filaments toward the center of the sarcomere, and we are making this sarcomere as shorter. Okay, so this is by the process of interaction. Okay. Again, that's the sarcomere. From this point to that point, Z discs, as you see. But we have in the middle of the sarcomere also a protein structure which is holding the thick filaments now, and we are calling it as line. Some maybe they are calling it disc. Where we are calling it disc or line, depends how you are viewing the structure. If you are viewing it in 3D, it is disc. If you are viewing it in 2D, it is line. That's the whole story with regard to the structure. Okay? Now, if you are taking transverse section at different levels of the sarcomere to say at this region where you have no overlap, okay, and you have only thin filaments, that's what you have. Here you have a region you are out of the M line, okay, out of the M line, you are taking the suction here at this point, you are getting the thick filaments as that structure. At the end line there, you have thick filaments with the structure of the end disc, okay? And at this region where you have overlap, what you are seeing, thick and thin filaments. But you can figure out actually each thick filament here is surrounded by 6 thin filaments around, and each thin filament is surrounded by 3 thick filaments. So the ratio of thin filaments to the thick filaments is 2 to 1. Okay, that's the ratio. Okay. Once you have contraction, please. So what you are getting shortening of the whole sarcomere. That's from this point to this point is the sarcomere, as you see, by sliding of thin filaments over thick filaments, you can get shorter sarcomeres, with more contraction, more shortening of these sarcomeres. Okay? But how we are getting the process of interaction and how we are getting the process of shortening. Before talking about this issue, we have to know the structure, the ultrastructure actually of the thin filaments, or the molecular structure of this stuff, the molecular structure of thin filaments, the molecular structure of thick filaments, okay? To understand the process of interaction between thick and thin filaments. So what you are seeing down here, they are thick or thin filaments. Thin filaments, and up you have thick filaments. Okay. Now, what's the ultrastructure of the thin filaments? It's composed of what? We have actin molecules polymerized in a way to form what we are calling the backbone of the thin filaments. In addition, we have other regulatory proteins, okay, which are also involved in the structure. We have this type of protein, which is called tropomyosin, and we have also another type, which is called the tropomins. Okay. Now, if you are viewing the actin molecule, they have a slide there in black. You are seeing it, which is called myosin binding site. Why we are calling it myosin binding site? We have this site interacting with myosin molecules. But if you are viewing the structure of the thin filaments, these myosin binding sites are covered by tropomyosin. Okay? So to get interaction between thick and thin filaments, you need to get these sites uncovered. And we can get this interaction. Now, what about thick filaments? Thick filaments are composed of this molecule, which is called myosin. The myosin is having 2 globular heads, is having also a tail, which is also an alpha helix structure, the tail. The tails are forming the backbone of the thick filaments, while the heads, as you see, they are protruding outside, forming a structure which is called the cross bridges. These are cross bridges. They are the heads of myosin. You can note here we have 2 sites over each head. One is called actin binding site. So this site is for interaction with actin molecule. And you have another site which is called myosin ATPase site. What's the function of that site? Is like an enzyme splitting ATP. Okay? Splitting ATP and phosphorylating the head. Now, once the head is phosphorylated, we can have high affinity for the sites for the cytonactin and the cytomycin having very high affinity for each other. If you have the heads dephosphorylated, what happens to that? We are having much less affinity between the two sides. You see the importance of this point, okay? Now, to get the interaction, we have needed another ion. What that ion is? Calcium, okay? Once you have high calcium concentration, this calcium will bind to what? Troponin. Troponin actually is having three subunits. We have troponin C, we have troponin T, and you have troponin I. Why we are calling them in that way? Troponin C for to interact with calcium. Troponin T is inserted to tropomyosin. I is the link between the two types of troponins, between the T and the C. Okay? Now, by increasing calcium concentration, you are getting that calcium binding to troponin C. Actually, you are needing 4 calcium ions to bind to one troponin C. By binding of 4 calcium ions to one troponin C, we are getting conformational changes in the regulatory proteins. These conformational changes results in displacement of tropomyosin away from the binding sites. Once you have displacement, now what happens to the binding sites? They are uncovered, and you can get interaction between thick and thin filaments, simply in that way, okay? So this is the process. We are needing calcium, which is important for the muscle contraction. You will see from where we are getting that calcium and how we are getting the release of calcium later on. Okay. So this is kind of summarize what happens at the level of the muscle with regard to the structure actually of the muscle and the components which are forming the thin filaments and the myosin heads and the myosin molecules actually and so on. You can go through that slide and then let's by yourself. Now again, once you have interaction, okay, of between heads and the side overacting, you have automatic, okay, tilting of the heads, automatic tilting. Any interaction you have that automatic tilting of the head, which results in pulling the thin filaments toward the center of the sarcomere. By pulling, as you see, we can get shorter sarcomeres. Okay? Not only shorter sarcomeres, we can get also changes in other configuration structures of the sarcomere. For example, what happened to the eye band? Also can be shorter. What happens to the axon? Shorter. What happens to the A-band? Not yet. A-band is corresponding to the presence of thick filaments. We are not getting short end of the thick filaments. Okay? So no change in the A-band, but we have changes in other structures of the sarcomere. So again, you have interaction. When you have calcium, once you have interaction, you have tilting or bending. Okay? Tilting or bending. By this bending, you are pulling the thin filaments toward the center of the sarcomere, then you have detachment. We will see this process in more detail. To represent what happens at the level of, or the, with regard to the interaction between thick and thin filaments. So what ion we have needed? Calcium. If you have calcium, you can have interaction. This process or this phase is called binding. Binding of thick or the head to the binding size of actin. بس لو سمحتوا واحد سكرنا الباب. This is followed automatically by another process, physiological process, which is tilting of the head toward the center of the sarcomere, which is called bending or power stroke. Some they are calling it power stroke. Okay? لو سمحتوا. Now, what happens to that? If you see here, the head is phosphorylated, and at the ATPase site, what we have? ADP. What happens if we have that head dephosphorylated? We can get detachment. Simply, we are getting the detachment process, okay? So that's the phase that we have. So what we are needing to get detachment, we are needing to replace this ADP with an ATP. In addition, we are needing to dephosphorylate that. Now, you remember we said we have ATPase site. What's the function of that ATPase site? Splitting that ATP and phosphorylating the head again. Okay? Once you have split that ATP and phosphorylate the head again, you are getting the heads of myosin returning back to their initial position, which is energized position, ready for new interaction. But that new interaction is not taking place only if you have high calcium concentration. If you still have high calcium concentration, you are getting that cycle again and again. If you have low or low calcium concentration, what happens? Everything in that position. No interaction between thick and thin filaments, and the muscle is in relaxation actually. Okay. Now what happens if you have no ATP in the muscle to replace the ATP? Everything is stuck at that position. Okay? We have a phenomenon, لو سمحتوا please. انتوا المجموعة الوحيدة اللي طالع لها صوت صراحة، المجموعة الأولى الصبح كانوا، والثانيين ولا واحد كان يحكي، كل جاي يتعلم، أما إذا في منكم ناس مش جايين يتعلموا هذا شيء ثاني. Please. So what happens if we have no ATP in the muscle? Everything is stuck at that position. The head is bound to the thin filaments, and it is in bending, okay? So what happens to the whole muscle? It is contractures of these muscles or stiffness of that muscle, and that can happen actually. This phenomenon first is called rigor mortis. So after a few hours of death, when there is no more ATP in the muscle, what happens to the muscles? Actually, there's contractures of these muscles, and that contracture because forming what we are calling rigor mortis as phenomenon. That's the rigor mortis. Some they are calling it as rigor complex, which is born. So this is what is happening at the level of the muscle and to this contractile process. You have a question?